Acid-base titrations. Titration is a technique. It's a laboratory technique used to find the concentration of a solution. So we take a solution with a known concentration and we react it with a solution with an unknown concentration. And we use solution stoichiometry to figure out the concentration. So for an acid-base titration, we're going to be doing acid-base neutralization reactions. And the net ionic reactions for these is always going to be the same. It's hydrogen ions from the acid and hydroxide ions from the base, and they combine together to form water. The anion on the acid and the cation on the base are just spectator ions, and they don't actually participate in the reaction. So let's look at some illustrations. So here is an illustration of a beaker containing hydrochloric acid. You might wonder, well, where are the chloride ions? Well, we're not interested in the chloride ions because they're spectator ions. So we're just going to look at the things that do something. So HCl, when you put it in water, ionizes to form hydrogen ions, and that's these little guys, and chloride ions, which we're ignoring. In the titration, what we do is we take, here we're taking sodium hydroxide and we're titrating the HCl with it. And so here in the burette, we have sodium hydroxide. Again, the sodium is a spectator ion, and so we're just showing the hydroxide ions. So we add hydroxide ions to our acid solution, and they combine in that net ionic reaction to form water molecules. And so we add sodium hydroxide, we add the hydroxide, and we add the hydroxide until it has reacted with all of the hydrogen ions. So we're doing a stoichiometric mixture here. We've got just the right amount of hydroxide and hydrogen ions together so that they all react. It turns pink because we put phenolphthalein in it, which is an indicator. The phenolphthalein will turn pink when there's just a tiny bit of extra hydroxide ions. So we're going a little past the stoichiometric mixture, but just a teeny tiny bit. We call this the equivalence point. The equivalence point is where the moles of hydroxide added equals the moles of hydrogen ions in the original sample. And it's also sometimes called the end point because that's where you stop. So when we know the concentration of the sodium hydroxide and we measure the volume, we know how many moles we added. That has to equal the moles of acid. And then if we know the volume of the acid solution, we can calculate the concentration. So we signal the equivalence point using an indicator, and that's a dye whose color depends on the acidity of this solution. So by carefully measuring the concentration of one and the volume of both, we can figure out the concentration of the other one. There's a picture, actual pictures, and this looks like what we did in lab. So we have a clear solution of sodium hydroxide in our burette, and we have a clear solution of hydrochloric acid in the flask. And we add, and as we're adding, we see a little bit of pinkness here, but then when we swirl it to mix it around, it disappears because the sodium hydroxide, the hydroxide ions are reacting with the hydrogen ions and forming water. When we've got just a little bit of extra hydroxide ions, then the solution turns pink, and that tells us we've added just enough. So here's an example of how to do these calculations. So the titration of a 20 ml sample of an H2SO4 solution of unknown concentration requires 22.87 milliliters of 0.158 molar KOH solution to reach the equivalence point. What is the concentration of the unknown H2SO4 solution? And that looks like kind of a big hairy problem, doesn't it? But we can break it down, and it's really not that bad. So all titrations are, in essence, a stoichiometry problem. For stoichiometry, it's really helpful to have